In this lecture, we will briefly look at the different types of capacitances associated with a MOSFET. So far, we have been assuming that the MOSFET is an infinitely fast device, and therefore the output drain current will respond almost instantaneously to the applied gate source voltage. But in reality this is not true, and therefore the MOSFET will have a certain delay associated with it, which we will model as capacitances. And if you look at the three-terminal model of the MOSFET that we have built so far, the MOSFET presents an open circuit between the gate and source terminals, and between the drain and source terminals it presents two components. One of them is the voltage control current source corresponding to the transconductance of the device, which is Gm times small VGS, which is the small signal gate source voltage, and it also presents a resistance which we will represent as RDS, which is due to channel length modulation. Now, to understand the capacitances of the device, we have to realize that the MOSFET also has a fourth terminal, which is the bulk terminal, or B, and there are various capacitances associated with the between the different terminals of the MOSFET. Now I will show the capacitances in blue on the same figure. So it turns out that the MOSFET has four capacitances associated with the device itself. So the first capacitance is the gate source capacitance, which we will represent as CGS. It also has a capacitance between the gate and drain terminals, which we will call CGT. It has two more capacitances associated with the bulk terminal. So there is a source bulk capacitance CSB, and there is a drain bulk capacitance CDB. As you can see, now due to these capacitances, the MOSFET will not respond instantaneously to any applied gate source voltage. There will be certain delays associated with the device. Now, just wanted to point out that in this course we will not be studying each of these capacitances in too much detail. The things we need to remember are that the largest capacitance associated with the MOSFET is CGS, and in saturation this CGS is approximately equal to 2/3 W times L times C aux, where W is the width of the gate of the MOSFET, L is the length of the gate of the MOSFET, and C aux is of course the oxide capacitance per unit area. This is normally the largest capacitance associated with the MOSFET. Now, obviously, each capacitance has a certain dependence on dimensions, has a certain dependence on also on doping concentrations, etc. So, but we will not worry about those things here. In this course, we will assume that every node has some capacitance to ground. We'll assume that every node of the circuit has some capacitance to ground. This will, you will find that this will make our job much easier. We will assume this only for circuit analysis, circuit and system analysis. And I also wanted to point out that normally, since we have not seen this bulk terminal too often before, normally this bulk terminal is connected to the lowest potential in the circuit if it's a p-type substrate, and therefore the drain bulk and source bulk capacitances have one node grounded. Now I also should tell you that CGD is normally a small capacitance, but it can become significant as the device gets smaller and smaller. Let us take a quick example to understand the effects of this capacitance. So we will take the simplest amplifier that we have always seen, which is a common source amplifier. So let us assume that we have a common source amplifier with a resistive load. So at the gate I apply the combination of a V bias, I'll call that VB, plus some small signal voltage Vs. Let us assume that this resistance is R. Now I need to assume the capacitances in the circuit. I'm going to make my job simpler by ignoring CGD for now. So I know that the significant capacitances in the circuit are going to be these two capacitors. Now I also know that those capacitances will come typically from devices connected to the terminal, but I will just call them C1 and C2 for now, because I just want to find out what happens to the circuit when I actually have capacitances from every node to ground. Because normally given the size of the device and given the device properties, I can calculate what C1 and C2 are. So for now at the system level I am just going to assume that there are capacitances C1 and C2. At low frequencies we know that the gain of the amplifier, which is VO by Vs, is minus Gm times R. This is of course true only at low frequencies, and I am also neglecting RDS in this particular expression, and normally RDS would be much larger than R. Now suppose you have capacitances C1 and C2. I now have to draw the new equivalent circuit, and I'll do that here. The small signal equivalent work circuit will look as follows. So Vs is directly applied across C1, which generates the gate source voltage. And again, for the purposes of this discussion, I am going to assume that RDS is much larger than R. In such a case, the output voltage is nothing but minus GMVGS into R parallel 1 over SC2. As you can see, there is since Vs is assumed to be an ideal voltage source in this case, the voltage appears directly across C1, and you can write VO in terms of Vs in this manner. Now what is the expression for VO by Vs? VO by Vs is nothing but minus Gm into this expression, and this can be further simplified in the following fashion. I am going to write it in two steps. The first portion is the small signal gain of the circuit in the absence of capacitances. In other words, it is the low frequency or DC gain of the circuit. So it's often called DC gain, even though it is not at DC. It is the low frequency gain of the amplifier, and that is of course multiplied by 1 plus SC2 R2. This gives you the frequency response of the circuit, which happens to go to 1 when you operate at very low frequencies. Now, as you can see in this particular case, the transfer function, which is the gain of the device, has a single pole response. So now let us quickly draw the Bode plot for this particular circuit. So if I were to draw the magnitude and phase response of the circuit, so I am going to plot VO by Vs, magnitude, and the angle of VO by Vs. At very low frequencies, which I am going to draw in black, or rather without the capacitances, the circuit looks ideal. It has a constant gain irrespective of frequency, whose magnitude is Gm times R. The phase of the circuit is now a constant value of minus 180 degrees. Now, with the capacitances C1 and C2, it turns out that this behavior is valid only at low frequencies, and at higher frequencies the magnitude of the gain goes down at minus 20 dB per decade, in this particular plot. Now I'll just point out that this is now in dB and not just the magnitude, and you're plotting it as a function of log of omega. And the pole frequency in this case is at 1 over RC2. And also this frequency at which the gain goes to 1 is often called the unity gain frequency, and that can easily be calculated from the previous expression here. What about the phase response? Now it turns out that in this particular circuit, at low frequencies the phase is still minus 180 degrees. So the circuit starts off at minus 180 degrees, but as we know, after it hits a little bit before it hits the pole at 1 over RC2, the phase starts to degrade, starts to reduce further, and that starts happening at approximately 1/10 of this frequency. And at the pole frequency, the pole should give a phase of exactly minus 45 degrees, and that will happen here. It will be at minus 225 degrees at the pole frequency, and at very large frequencies the pole should contribute 90 degrees, and therefore it should asymptotically go to minus 270 degrees. So the phase response will look something like this. Now, as you can see, the circuit looks the circuit or the phase response or the magnitude response looks nothing like the low frequency equivalent when you start increasing the frequency to really large values that are comparable or larger than 1 over RC2, which is the pole frequency of the system.